Hey, my name is Mike. I'm a developer from Philadelphia, and in this video, we're going to answer the question, why object-oriented programming? In order to answer that question, we'll take a look at object-oriented programming as a programming paradigm and compare it to two other popular programming paradigms. We'll also take a look at the four pillars of object orientation. So without further ado, let's get into the video and get started. In the early days of computing, most programs developers were writing were simple and fairly straightforward. But as computers started to become faster and more powerful, the complexity of the programs developers were writing increased. So as code became more and more complex, programming languages and best practices evolved to suit the needs of developers. Eventually, these evolutions in languages and best practices led to what we now call programming paradigms. A programming paradigm is a specific style of organizing and writing programs with the goal of increased organization, less bugs, and better code maintainability. In this video, I'll be discussing one of the most popular programming paradigms used today, object orientation. We'll take a look at some of the features of object orientation and look at how it compares to other popular paradigms. First, it'll help to have an example we can use to illustrate these concepts. So let's imagine a simple to-do list program. This program would allow users to keep track of tasks they need to complete throughout their day. Each task would have a description and a status, whether or not it's complete. Now, before we dive into object orientation, let's take a step back and examine what exactly makes up a program. All programs have data and behavior. The data is what the program knows. In the case of our to-do list, that's the name of the tasks and whether or not they're complete. The behavior is what the program can do with its data. In our to-do list program, we can toggle whether or not a task is complete. So we can toggle a task as complete or incomplete. So in this case, we have two pieces of data and one behavior. This data and behavior makes up the core of what our program will do. To really get a grasp on object orientation as a programming paradigm, let's take a look at it alongside two other popular programming paradigms, procedural programming and functional programming. In procedural programming, the data and the behaviors are spread out into the same set of step-by-step instructions. When we need to use the behavior, in this case, toggling a to-do task, we can manipulate the data directly, thus changing the overall state of our application. In procedural programming, the order of our code matters very much, and our data is mutated directly as the program carries out its behavior. In functional programming, the data and the behavior are kept separate. When we want to use our behavior and toggle the to-do task, instead of mutating the data directly, our behavior will be abstracted into a pure function, which takes our data in as an input and returns an updated copy of our data as an output. In functional programming, we never mutate the data directly. Instead, we rely on pure functions to return a new copy of the updated data. That's a little about procedural and functional programming paradigms. Now let's see how object orientation handles data and behaviors. In object-oriented programming, the data and the behavior is grouped together in objects. An object is a special entity in our code which combines all of the data or attributes as well as all of the behaviors or methods into an easy-to-use container. When we want to access the data or use the behaviors, we do so through the object. In the case of the To-Do app, we might create a task object for each task in our program, which would keep track of the name and complete status of the task and would also know how to toggle it. Now that we've taken a look at object orientation compared to other popular paradigms like procedural and functional programming, let's dive a bit deeper and talk about the four pillars of object orientation. These are four characteristics of object orientation, namely encapsulation, abstraction, inheritance, and polymorphism, which provide endless benefits to developers and are responsible for object-oriented programming success in the development world. The first pillar is encapsulation. Now you'll recall when we created our to-do list using object orientation, we combined all of the data and behavior for a to-do task into a single object. In reality, we would define a task class and then create task objects based on what's in the class. These objects will then keep track of the to-do list description, complete status, and also the functionality around toggling the complete status in one simple container. The first pillar, encapsulation, refers to an object's ability to do exactly this, to bundle together related data and behavior and limit data scope. So not only does keeping the data and behavior together like this make it easy for programmers to make sense of the data and behavior involved in a task, it also prevents code outside the object from seeing how it works or modifying it in undesirable ways. The task is now encapsulated into its own entity, and can choose how it wants to interact with other code and what aspects of its behavior it wants to expose. Without encapsulation, you'd still need to keep track of the data and behavior related to a task, but it would be all jumbled throughout your program. You might have the task's name in one place, its complete status in another, and the function for toggling it in another. And that's just for one task. Imagine if your program needed to keep track of hundreds or thousands of tasks. Your code would soon resemble a plate of spaghetti. Encapsulation bundles data and behaviors together that should be together and makes it easy for that data and behavior to be used by other parts of our code. The second pillar of object orientation is abstraction. Abstraction is object-oriented programming's ability to hide complex logic from the user, making the code that we write easier to use in other places. A good example of abstraction in the real world is sending an email. When you send an email, you open up your email client, type out a message, and click send. It's as simple as that. You don't need to know anything about email servers or the way emails get encoded or formatted or transferred over the internet. That entire process is abstracted away from you, and you just have to hit the send button. By placing all of the complex logic of our programs in classes, just like with emails, we're able to abstract it away from the people using our code and make everyone's life easier. In our task class, we've abstracted away the logic of toggling the isComplete state. In reality, to toggle this value, we may need some complex code, maybe an if statement to check the current complete status, some logic for updating that value, or some other checks to maybe make sure the current user has permission to toggle it. But if we're using a task object in our code, none of that matters. All we need to do is call the object's toggleComplete method, and we get the same effect. We don't need to know anything about how this is getting toggled or the logic behind when it can and can't be toggled. We just call the class method and it works. In this case, we've abstracted away the logic behind toggling the complete status on a task, ultimately making it easier for other pieces of code to perform that action. Now that we've taken a look at the first two pillars, let's take a look at the third, which is inheritance. In object-oriented programming, inheritance allows a class to inherit all of the functionality of another class. This allows us to share code between multiple classes and reduce the amount of code that needs to be written overall. Now that we've built version 1 of our to-do app, let's suppose we wanted to add an additional type of task to the app. This would work like a normal task, except it would have a deadline on it. This special type of task can be called a deadline task. In addition to having all the attributes and methods of the normal task, the deadline task will also have a deadline attribute, which would be a date or a time, and an isOverdue method, which would tell you whether or not it's currently overdue. Now you might think that in order to create this new deadline task, we'll have to copy and paste all of the code from the task class into the deadline task class. But thanks to inheritance, we actually don't. As I mentioned, inheritance allows a class to inherit all of the attributes and functionality of another class. Therefore, we can use inheritance to have the deadline task inherit all of the attributes and functionality of the task class. This means that we don't have to re-implement or rewrite any of that logic. All of that will automatically be available to any of the code interacting with a deadline task. Therefore, users of the deadline task objects will be able to work with them and toggle them complete or incomplete, just like with a normal task, without us having to rewrite any of that code. Generally, inheritance works best in situations like this, where you have an entity like a deadline task, which is just a more specific version of another entity like our task class. The final pillar of object-oriented programming is polymorphism. The word polymorphism literally means having multiple forms. In object-oriented programming, when we use inheritance in our classes, we can take advantage of polymorphism when using these classes. To help make sense of this, let's take a close look at our two tasks. First, we have a general task defined in the task class. Then we have a deadline task, a more specific type of task, which inherits all of the functionality and attributes of the task class. Let's suppose we had two objects. One is a task called myTask, and the other is a deadline task called myDeadlineTask. In order to understand polymorphism, we have to look at these objects in terms of their data types. Remember that when we create a class, we're actually creating a new data type. The first object, myTask, is the task data type. It's an implementation of the task class, which makes it a task type. The second object, myDeadlineTask, is a deadline task data type. It implements the deadline class. But because the deadline task inherits all of the attributes and functionality of the task class, the myDeadlineTask object is also a task data type. If you think about it, this makes sense. The myDeadlineTask object has all the same attributes and methods as the myTask object, along with a few more specific ones related to deadlines. So any code that's designed to work with a task object will also be able to work with a deadline task object. This, in a nutshell, is polymorphism. It's what allows us to use either a normal task object or a more specific deadline task object in our programs interchangeably. So anywhere a task object would go, a deadline task could also go. So there we have it, the 4 pillars of object-oriented programming. We have encapsulation, which allows us to bundle together related data and behavior and limit data scope. Abstraction, which allows us to hide complex logic from the user and make our code more accessible. Inheritance, where a class can inherit all the functionality and attributes of another class. And polymorphism, the idea that 2 or more classes can be of the same type and used interchangeably. Understanding the 4 pillars is the first step towards mastering any object-oriented programming language, and by taking advantage of the concepts exposed by these pillars, you can write software that is scalable, clean, and as bug-free as possible. Thanks for watching. I hope you learned something, and I'll see you next time.